In this lecture, I am going to present what is stiffness matrix, and what is displacement method of analysis, and what are the different steps used to determine the internal member forces of a structure. Then I will solve one problem. First we have to know what is stiffness. The stiffness is defined as the force required for a unit displacement. Similarly, the stiffness of a spring is defined as the force K11 required for a unit displacement at coordinate 1. So, what is the force required at coordinate 1? Due to the unit displacement at coordinate 1, so that is called the stiffness. This is denoted by the K11, that is the force required at 1 due to the unit displacement at coordinate 1, K11. K11 is equal to P1 by delta 1. This is called the stiffness. Then coming to the stiffness matrix. What is stiffness matrix? So, stiffness matrix is a square matrix K, that is denoted by K. K is equal to K11, K12, K1j, K1n, K21, K22, K2j, K2n, Ki1, Ki2, Kij, Kin, Kn1, Kn2, Knj, Kn. These are the stiffness coefficient. K11, K12, these are the stiffness coefficient. In order to generate the jth column of the stiffness matrix, a unit displacement must be given at coordinate j. Unit displacement must be given at coordinate j without displacement at other coordinates, and the force required at all the coordinates are determined. What is the force at coordinate 1? Due to the unit displacement at coordinate j. So, this is the stiffness coefficient K1j. Similarly, what is the meaning of K2j? So, this is the force at coordinate 2 due to unit displacement at coordinate j. This is K2j. That is, to generate the jth column of the stiffness matrix, a unit displacement must be given at coordinate j. Unit displacement must be given at coordinate j without any displacement at other coordinates. At other coordinates there is no displacement, and the force required at all the coordinates is to be determined. Then what is the displacement method of analysis? The displacement method is also known as stiffness method or the equilibrium method. In this method, the degree of kinematic indeterminacy, that is degree of freedom of a structure, is determined first, and the coordinates is assigned to each independent displacement components. In general, the displacement components are the support and joints are treated as independent displacement components. Let 1, 2, n are the coordinates assigned to these independent displacement components delta 1, delta 2 and delta n. First, lock all the support and joints to obtain the restraint structure in which no displacement is possible are the coordinates. First, you have to lock all the supports and joints and to make the structure restraint, and there is no displacement possible are the coordinates. Then find out P1 dash, P2 dash, Pn dash, the forces are the coordinates 1, 2, n in the restraint structure in which the displacement delta 1, delta 2, delta n is equal to 0. Let the supports and joints be unlocked and permitting displacement delta 1, delta 2, delta n are the coordinates. These displacement required forces P1 delta, P2 delta, Pn delta at coordinate 1, 2, n respectively. If P1, P2, Pn are the external forces at coordinates 1 to n. Then the condition of equilibrium of the structure may be expressed by the equations P1 is equal to P1 dash plus P1 delta, P2 is equal to P2 dash plus P2 delta. Similarly, Pn is equal to Pn dash plus Pn delta. This is expression 1. Then equation 1 may be expressed in the matrix form. So you can express this equation in matrix form. P is equal to P dash plus P delta. This is 2. But we know P1 delta is equal to K11 delta 1 plus K12 delta 2 plus K1n delta n. Similarly, P2 delta is equal to K21 delta 1, K22 delta 2 plus K2n delta n. Pn delta is equal to Kn1 delta 1 plus Kn2 delta 2 plus Kn delta n. After putting the above values in equation 2, we get, after putting these values in equation 2, we get P1 is equal to P1 dash plus K11 delta 1 plus K12 delta 2 plus K1 delta n. P2 is equal to P2 dash plus K21 delta 1 plus K22 delta 2 plus K2n delta n. Pn is equal to Pn dash plus Kn1 delta 1 plus Kn2 delta 2 plus Kn delta n. Equation 3 may be expressed in the matrix form. P is equal to P dash plus K into delta. This is P matrix and this is P dash matrix and this is K into delta. This is K into delta matrix. Solving equation 4 for the unknown independent displacement components, delta is equal to K inverse P minus P dash. This is equation 5. If the external forces act only at the coordinates, the term P1 dash, P2 dash, Pn dash vanish. Then the equation 5 becomes, so after taking the P dash is equal to 0, the equation delta is equal to K inverse into P. On the other hand, if there are no external forces at the coordinates, then P1 is equal to P2 is equal to Pn, that is equal to 0. Then the equation 5 becomes delta is equal to minus K inverse P dash. This is 7. After the computation of displacement, after computation of the displacement using the expression 7, then the bending moment in the member of the structure may be calculated using the slope deflection equation. This method is applicable to statically determinate as well as indeterminate structures. This method is known as displacement method because in this approach the displacements are treated as unknowns. Also, this method is called the stiffness method because the stiffness matrix is used, that's why this is called the stiffness method. As the condition of equilibrium of the structure is utilized for the determination of displacement, so the method is also known as equilibrium method. Then what are the steps used to solve the structure by displacement method of analysis? So these are the different steps. First, determine the degree of kinematic indeterminacy, that is also called the degree of freedom. Then identify the independent displacement components. Then assign the coordinates 1 to n to the independent displacement components. Then prevent all the independent displacement components to obtain the restraint structure. Then find out P dash, the forces required at the coordinates in the restraint structure due to the loads other than those acting at the coordinates. So this is the force you have to find out. What are the load is given other than the load at the coordinates. Then determine P delta, the forces required at the coordinates in the unrestrained structure to cause the independent displacement component delta. Then you have to apply the displacement, unit displacement at the coordinate, at one coordinate. Then you have to find out what are the forces at all the coordinates. Then you have to apply the unit displacement at other coordinates. Similarly, you have to find out what are the forces at all the coordinates. So this becomes the stiffness matrix. So compute the net forces at the coordinates. So what are that formula? P is equal to P dash plus P delta. Then by using the condition of equilibrium of forces to compute the displacements. So delta is equal to K inverse P minus P dash. Knowing the displacements, compute the internal member forces by using the slope deflection method. So after getting the unknown displacement, then you can compute the internal member forces by using the slope deflection method. Then coming to one problem, here we will solve one problem, frame structure using the displacement method. So this is the frame structure, ABCD, and AB length is 4 meter and BC length is 8 meter, then BD length is 4.8 meter, and on the column BD there is having one horizontal load 120 kilonewton at a distance 3.2 meter from the support D and 1.6 meter from the point B, and the moment of inertia for AB, BC and BD is given. For AB the moment of inertia is I, and for BC the moment of inertia is given 2I, and for BD the moment of inertia is given 3I. So here you see at joint C, due to the fixed end there is no displacement takes place, and at a joint D also due to the fixed end there is also no displacement takes place. This is restraint against the three displacement component, that is in vertical, horizontal and rotational. So there is no displacement takes place at C and D. But here at support A, due to the hinge support, there is no displacement takes place in vertical direction and in horizontal direction. Only the rotational displacement takes place. So here you have to take one rotational displacement at A. Similarly at B, there is also the rotational displacement takes place. At B also there is the rotational displacement takes place. So here there are two rotational displacement takes place at A and B. Two rotational displacement takes place at A and B. So you have to assign the coordinates at A and B. You have to assign the coordinate at A and B. The number of coordinates is equal to the number of rotational displacement. So here there are two displacement takes place. So you have to choose the two coordinates and you have to assign the two coordinates at A and B. Then what you have to do? So first you have to make the structure is a restraint structure by removing all the displacement. So here there is rotational displacement takes place, and here also there is the rotational displacement takes place. So you have to make the structure is restraint structure. So you have to make all the supports are fixed. You have to make all the supports are fixed. Means there is no displacement takes place at any support. There is no displacement takes place at A, there is no displacement takes place at B, there is no displacement at C, and there is no displacement at D. So this is the restraint structure. So you have to find out what are the force required at the coordinates 1 and 2 in the restraint structure due to load. So what are the load given due to that load? You have to find out what are the forces at the coordinate 1 and at the coordinate 2. So this is the coordinate 1 and this is the coordinate 2. This is coordinate 1 and this is coordinate 2. So you have to find out the forces at the coordinate 1 and 2 due to the applied load. Due to the given loading, you have to find out what are the forces at coordinate 1 and 2. in the fully restrained structure. So, this is the figure of the fully restrained structure, and the coordinate is given here, one coordinate, and this is the another coordinate. This is two coordinates. So, this is one coordinate at A. So, this is another coordinate at B. So, this is the first coordinate at A, and this is the second coordinate at B, 1 and 2. This is 1 and this is 2. This is the coordinate 1 and this is the coordinate 2. This is coordinate 1 and this is coordinate 2. So, you have to find out the forces required at the coordinates in restrained structure. So, what you have to do, there is no load on the span AB. So, the moment, the fixed end moment, you have to find out MFAB and MFBA is equal to 0. Similarly, there is no load on the span BC. The fixed end moment at the end B and C, MFBC and MFCB, that is also 0. But on the vertical member BD, there is having the one concentrated load, 120 kilonewton, at a distance 3.2 meter from D and 1.6 meter from B. So, due to this load, you have to find out what is the fixed end moment here and here, MFDB and MFBD. So, MFDB is equal to minus W into A B square by L square, minus 120 into 3.2 into 1.6 divided by 4.8 square. This is minus 120 into 3.2 into 1.6 square by 4.8 square is equal to minus 42.667 kilonewton meter. Similarly, find out the MFBD. Here, what is the fixed end moment? MFBD is equal to plus 120 into A square B by L square, plus 120 into 3.2 square into 1.6 divided by 4.8 square. 3.2 square into 1.6 by 4.8 square. So, this is equal to 85.333 kilonewton meter. Then MFAB, MFBA, MFCB, MFBC, that is 0 because there is no loading on the span AB and on the span BC. So, this is the moment only you will get at D and at B due to this load, MFDB and MFBD, only these two moments. And you have to find out what are the forces developed in the coordinate direction due to the given loads. So, this is the coordinate 1 and this is the coordinate 2. This is coordinate 2. So, you have to find out what is the forces, what is the force at the coordinate 1. But here you see, so what are the moments, fixed end moment you are getting. So, here the fixed end moment MFAB, that is equal to 0. So, this is the force at the coordinate A, coordinate 1, the force at the coordinate 1 is also equal to 0. P1 dash is equal to MFAB is equal to 0. Then at the coordinate 2, what is the force? So, here you see the force at the coordinate 2 is equal to MFBA, MFBC and MFBD. So, what is the fixed end moment you got from this span here at B, and what is the fixed end moment you got from this span at B, and what is the fixed end moment you got from this span at B. These three fixed end moment is equal to the force at the coordinate 2. So, here P2 dash is equal to MFBA, MFBA plus MFBC plus MFBD, MFBC plus MFBD. This is equal to 85.333 kilonewton meter. So, here you got the force at coordinate 1 and coordinate 2. So, here there is no moment, the fixed moment here is your 0. So, this is equal to the force at coordinate 1, but here at force at coordinate 2 is equal to the fixed moment BA, fixed moment BC and fixed moment BD. What is the moment you got here, here, here. So, this the summation of these three moments is equal to the force at coordinate 2, P2 dash. Then coming to how to find out the forces in the unrestrained structure. So, what you have to do, you have to apply the unit displacement at coordinate 1 Then you have to find out what is the force at the coordinate 1 and 2. Then you have to apply unit displacement at the coordinate 2, and you have to find out what is the force at the coordinate 1 and 2. And that becomes the stiffness matrix. Let us take the unit displacement at coordinate 1. So this is coordinate 1 and this is coordinate 2. So let us take the unit displacement at coordinate 1. Theta is equal to 1. And due to this unit displacement, find out what is the force at coordinate 1 and what is the force at coordinate 2. So this is the fully restrained structure with unit displacement is given at coordinate direction 1. So here what you have to do, you have to make this is your unrestrained. You have to make the support A is unrestrained and the other supports are restrained. Hence other supports are fixed. You have to give here the unit displacement. Theta is equal to 1. And due to this unit displacement, you have to find out what is the force at A and what is the force at B. That is, what is the force at the coordinate 1 and what is the force at the coordinate 2. 1 radian rotation is given to support A in coordinate direction 1. Then forces developed in coordinate direction 1 and 2 are found. So what are the end conditions? Because here you see theta A, because here this is the A support and here the displacement is equal to 1. Theta A is equal to theta is equal to 1. Theta A is equal to theta is equal to 1. But here there is no displacement because this is your fixed. So here there is no displacement. So theta B is equal to 0. Take theta A 1 and theta B 0. Theta A 1, theta B 0. Then apply slope deflection equation and determine the forces. Then using the slope deflection equation, you have to find out what is the force here at coordinate 1 and what is the force at coordinate 2. So this is the force at coordinate 1, K11, I mean the force at coordinate 1 due to unit displacement at coordinate 1. The first subscript indicates the force at coordinate 1 and the second subscript, this is the unit displacement at coordinate 1. So K11 is equal to, this is, so you have to find out here K11, force at coordinate 1 due to unit displacement at coordinate 1. So this is equal to, you know from the slope deflection equation, 4 EI theta A by L plus 2 EI theta B by L. So 4 EI theta A, L is given here 4 meter, 4 EI theta A by 4 plus 2 EI theta B by 4. So theta A is equal to theta A is equal to 1 and theta B is equal to 0. So here you have to put theta A 1 and theta B 0. So after putting this value, so here you will get 4 EI by 4. So K11 is equal to EI. Similarly, find out what is the force at the coordinate 2 due to unit displacement at coordinate 1. So due to this unit displacement at coordinate 1, what is the force at the coordinate 2? This is the coordinate 2. So what is the force here? K2 due to the unit displacement at coordinate 1. So K21 is equal to, so what is the slope deflection equation here? 4 EI theta B by L plus 2 EI theta A by L. 4 EI theta B by L, L is equal to 4 and 2 EI theta A by 4. So here after putting the value of end condition theta A, theta B, theta A is equal to 1 and theta B is equal to 0. So here you will get K21 is equal to 2 EI by 4. Then after simplification, K21 is equal to 0.5 into EI. Then apply unit displacement in coordinate direction 2. Then apply unit displacement in coordinate direction 2. So this is coordinate 1. So by applying unit displacement at coordinate 1, this one, so here you got what is the force at coordinate 1 and what is the force at the coordinate 2 due to the unit displacement at coordinate 1. Similarly, apply the unit displacement in coordinate direction 2 and due to this unit displacement, find out what is the force at coordinate 1 and what is the force at coordinate 2. This is the figure. Figure 4, fully restrained structure with the unit displacement in coordinate direction 2. Apply here unit displacement in coordinate 2 and due to this unit displacement, find out what is the force at coordinate 1 and what is the force at coordinate 2. That is, you have to find out K12 and K22. You have to find out K12 and K22. 1 radian rotation is given to support B in coordinate direction 2, then forces developed in the coordinate direction 1 and 2 are found. So what are the end conditions here? Because here you see you have given the displacement at coordinate 2, this is theta is equal to 1, you have given, that is theta A, theta B is equal to theta is equal to 1. Then the displacement at other points, other supports A, D and C, that is 0. So here there is no displacement, the rotational displacement at A is 0, rotational displacement at C is 0 and rotational displacement D 0. So here there is no displacement at A, D and C, only the displacement at B, that is equal to 1. Theta B is equal to theta is equal to 1 and all other displacements are 0. Then apply slope deflection equation, determine the forces. So first you find out what is the force at coordinate 1 due to the unit displacement at coordinate 2, K12. K12 is equal to 4 EI theta A by 4 plus 2 EI theta B by 4. 4 EI theta A by 4 plus 2 EI theta B by 4. But here you see theta A is equal to 0. Here theta A is equal to 0 and theta B is equal to 1. So here you put this value, theta is 0 and theta B 1. So K12 is equal to 2 EI by 4. Then after simplification K12, this is K12, K12 is equal to 0.5 EI. Then find out K22. K22, that is the force at coordinate 2 due to unit displacement at coordinate 2. So here you find out using the slope deflection equation what is the force from AB span, from BC span and from BD span. K22, force at coordinate 2 due to unit displacement at coordinate 2. So this is from the AB span. So from AB span, here this is 4 EI theta B by 4 plus 2 EI theta A by 4. 2 EI theta by 4 plus 4 EI theta B by 4. Then from this span, BD span, here 4 EI theta B by this one 4.8. Then this is 2 EI theta D by 4.8. But here the I is given 3I. For BD span, I is given 3I. So you have to put 3I. 2E into 3I theta D by 4.8 plus 4E into 3I theta B by 4.8. Then take for span BC, what is the slope deflection equation. So K, this is this one is 2E here, this is 2E, 2I into theta C divided by 8 and from this side 4E into 2I theta B by 8. 4E into 2I theta B by 8, 2E into 2I theta C by 8. So these are the forces at coordinate 2 due to unit displacement at coordinate 2 from these three members. Then after putting the value of theta A, theta C, theta D is equal to 0 and theta B is equal to 1. So finally, so you will get this is the expression and the K22 is equal to 4.5 EI. So here you got by applying the unit displacement at coordinate 1. So here you got the force at the coordinate 1 and force at the coordinate 2. Similarly, by applying the unit displacement at coordinate 2, so here you got the force at coordinate 1 and force at coordinate 2. Then these 4 K11, K12, K21, K22. So this become the stiffness matrix. These 4 stiffness coefficient become the stiffness matrix. Finally, the forces acting in coordinate direction 1 and 2 are 0. But here in the question, so there is no forces acting in coordinate direction 1 and 2. Here you see the question. So here there is no force at coordinate 1 and there is no force at coordinate 2. If there is no force at coordinate 1 and 2, then what you have to do? P is equal to, you have to take P is equal to 0 0. If the forces acting in coordinate direction 1 and 2 are 0, you have to take P 0 0. Hence the stiffness equation becomes P is equal to, this is the stiffness equation, P is equal to P dash plus K delta, then K delta is equal to P minus P dash, P minus P dash, then K is equal to stiffness matrix, you have to put K11, K12, K21, K22. Here you got K11 value, here you got K11 EI, then K12 0.5 EI. So after taking this EI common, 1 0.5, similarly K21, K22, K21 you got here 0.5 EI and K22 you got 4.5 EI, 0.5, 4.5. So EI, this is the stiffness matrix, then delta, this is the two coordinate, delta 1 and delta 2, then P, there is no external force, the external force is 0, so you have to take P is equal to 0 0, then this is P dash. So this is the forces at coordinate 1 due to the applied loading, due to the given loading. So already you got this P dash, P dash is equal to P1 dash, P2 dash, this is the column matrix, P dash is your P1 dash, P2 dash, P1 dash, P2 dash, 0 and 85.333, 0, 85.33. This is P dash 0, 85.33 column matrix, and at the coordinate there is no external forces, so you have to take this is 0 column matrix, and this is the stiffness matrix, and this is the column matrix of the displacement at coordinate 1 and 2. Then this is EI 1 0.5, 0.5, 4.5, delta 1 delta 2 is equal to 0 minus 85.33. Then you have to take the inverse of the matrix, stiffness matrix, this one. Then you can find out what is the displacement at coordinate 1 and displacement at coordinate 2. Delta 1 delta 2 is equal to 1 by EI, and this is the inverse of the stiffness matrix into 0 minus 85.33. So after taking the inverse matrix here, then you have to multiply with this matrix, column matrix, then you can find out what is the displacement at coordinate 1 and displacement at coordinate 2, delta 1 and delta 2, that you can find out. So delta 1 delta 2 is equal to this one, the inverse matrix, 1 by 1 into 4.5 minus 0.5 into 0.5, then 4.5 minus 0.5 minus 0.51, and this is the column matrix 0 minus 85.33. Then after multiplication of these two matrices, you will get what is the displacement at coordinate 1 and displacement at coordinate 2. So this displacement delta 1 is equal to theta A, the rotational displacement at A, and delta 2 is equal to the rotational displacement at B. So here you got the rotational displacement, here you got the rotational displacement at A is equal to 10.039 by EI, this one 10.039 by EI, theta A is equal to delta 1, then theta B is equal to delta 2 is equal to minus 20.078 divided by EI, and that the rotational displacement at C and D is 0 due to the fixed end. Then after getting the rotational displacement at A and B, then you can find out what is the moment using the slope deflection equation. You can find out the final moment at the end of each member using the slope deflection method. Already you know what is the fixed end moment from the external loading. Then you have to take the, you know, the theta A, theta B, theta C, theta D. Here you got theta A, theta B, these two unknown independent displacement component, and theta C, theta D is equal to 0. Then after putting theta A, theta B, theta C, theta D and the fixed end moment, then using the slope deflection equation you can find out what is the moment. So MAB is equal to MFAB plus 4EI theta A by 4 plus 2EI theta B by 4. MFAB you know this is 0, already you got here starting here MAB is equal to MFAB 4EI theta A by 4 and plus 2EI theta B by 4. Similarly, MBA is equal to MFBA plus 4EI theta B by 4 plus 2EI theta A by 4. Similarly, find out MBC. MBC is equal to MFBC plus 4EI theta B by 8 plus 2EI theta C by 8. Similarly, find out MCB. MCB is equal to MFCB plus 4EI theta C by 8 plus 2EI theta B by 8. Similarly, find out MBD. MBD is equal to MFBD plus 4EI theta B by 4.8 plus 2EI theta B by theta D by 4.8. Similarly, MDB. MDB is equal to MFDB plus 4EI theta D by 4.8 plus 2EI theta B by 4.8. So, using this formula you can find out what is the final moment. So, here already you know the fixed end moment here, MFDB, MFBD, this is value, and MFAB, MFBA, MFCB, MFBC is equal to 0. MFAB plus 4EI theta A by 4 plus 2EI theta B by 4. Then after putting the value and theta A theta B value, then you will get MAB is equal to 0. Already you know this is the simply supported end, so MAB is equal to 0, you know. Then MBA, MFBA plus 4EI theta B by 4 plus 2EI theta A by 4. So MBA is equal to MFBA 0 plus 4EI by 4 into minus 20.078 by EI plus 2 EI by 4 into 10.039 by EI. Here MBA value is minus 15.059 kilonewton meter. Then MBC is equal to MFBC plus 4E into 2I theta B by 8 plus 2E into 2I theta C by 8. MFBC is 0, then here you put theta B and theta C. Theta B you got minus 20.078 by EI, theta C 0. After simplification, MBC is equal to minus 20.078 kilonewton meter. Then MCB is equal to MFCB plus 4E 2I theta C by 8 plus 2E into 2I theta B by 8. You know MFCB is equal to 0, then 4E into 2I by 8 into 0 plus 2E into 2I by 8, and this is that theta B value. Then after putting this, MCB is equal to minus 10.039 kilonewton meter. Then find out MBD. MBD is equal to MFBD plus 4E into 3I theta B by 4.8 plus 2E into 3I theta D by 4.8. Then after putting MFBD, theta B and theta D value, so here you get MBD is equal to 35.138 kilonewton meter. Then find out MDB. MDB is equal to MFDB plus 4E into 3I theta D by 4.8 plus 2E into 3I theta B by 4.8. Then after putting the value of MFDB, theta D, theta B, so finally you will get MDB is equal to minus 67.76 kilonewton meter. So these are the final moment. Then after knowing the final moment, so you can draw the bending moment diagram. First you have to apply the direction of the moment, then you can plot the bending moment diagram due to the support moments. Then the free bending moment diagram you have to find out. You have to draw the free bending moment diagram. Then after combining this free bending moment and support moment, then you will get the final bending moment diagram. Now all are clear how to solve the frame using the stiffness matrix method or displacement method.